Greetings! Tomorrow, Friday, February the 24th, will be our third Friday Flip Days, so I'm going to see all of you in the STEM foyer. But until that time, you may want to think about getting together with your poster group and getting a draft submitted for your hypothesis. Remember, you can submit that on the YO Courses assignment that's dedicated to that purpose. And homework 4 will be due on Tuesday, so that would also be something great to bring with you to Friday Flip Day. And don't forget that I have an office hour immediately following Friday Flip Day, and so we can continue our work on homework number 4 during that office hour. Great time to talk and work with others. In terms of lab, you'll want to continue working on your skill tests. I know some of you have been doing an amazing job of continuing your effort and sustained effort on those skill tests. So I will get started without further ado. And remember, when we left off last time, we had been talking about enzymes and enzyme regulation. And we had just begun this notion of competitive inhibition that can be caused by drugs. So that's where we're going to jump in today. So this is different than regulation, but it's equally as important because when we design drugs, we design inhibitors. That is, when we want to stop a bacterium from synthesizing its peptidoglycan, we design antibiotics that target the enzyme that builds, for example, the tetrapeptide chain in peptidoglycan. So we know that penicillin does that. So we know nature designed that one, but we also will design inhibitors that are competitive inhibitors of enzymes. That is, they literally get in the way of the binding of the substrate to the active site. This picture is helpful because it shows you that the substrate would bind to the enzyme at this active site. But notice that the inhibitor is equally as equipped to bind at that active site. So we could see a situation where the inhibitor would compete for binding with the substrate at that active site. So let's see who wins out. Oh, inhibitor gets it. So you might ask the question of what's going to dictate that. Is it going to be based upon, some sort of tug of war for that active site? What's going on? Well, there's actually two things. One is concentration. So if there's much more inhibitor in the environment, then it's going to win out more often. But also the other is affinity. So the enzyme will be more likely to bind to an inhibitor if it has overall a higher desire for that inhibitor. Now, if we think about why that could possibly be, like why would you ever have an inhibitor that could bind more tightly to an enzyme than its own substrate? Well, remember that an enzyme, what it does is it stabilizes the transition state. And in fact, enzymes bind more tightly to their transition state than they do to their substrate. So if you could be a brilliant organic chemist and you could actually design an inhibitor that looked more like the transition state than it did like the substrate, you would be designing an inhibitor that the enzyme would desire more than it desires its substrate. So there actually are inhibitors that bind more tightly to the enzyme. So many drugs that are designed to kill or inhibit the growth of a microorganism are competitive enzyme inhibitors. Penicillin is a great example of that, but so too are the sulfa drugs. So sulfa drugs competitively inhibit the enzyme that builds folic acid. So we come back to our ingredient list on that vitamin, and remember that we have to take folic acid in our diet. So it doesn't bother us if we don't have the enzymes to make folic acid, but bacteria do. So we can inhibit their ability to make folic acid, and we don't care because we've lost that pathway long since, evolved to not utilize or make our own folic acid. We have to take it in our diet. So we can recognize then that it doesn't affect us to have folic acid, at least not directly, the inhibition of the folic acid biosynthesis pathway, but it does impact bacteria. So you can answer this question, analogs of what structure make good competitive inhibitors and why. I want to talk too about non-competitive inhibitors because there are inhibitors that bind at a site other than the active site on an enzyme They might bind somewhere on the exterior of a protein, and because they bind and trigger changes in the conformation, they may act in a way to inhibit, but they aren't directly competing with the substrate of the enzyme. A good example of this is toxic heavy metals. For example, silver can bind at the R groups of cysteine. It actually binds to the sulfhydryl, and it triggers conformational change, and that triggers inhibition. So both competitive and non-competitive inhibition can be either reversible or irreversible, meaning that if it's irreversible, it is completely stopping and killing the enzyme. There is no recovering that enzyme. So it's a covalent linkage that causes damage that can't be undone. Penicillin is irreversible. It's competitive and irreversible. The other good example of this is to think about painkillers, and I know this maybe doesn't seem inherently related to micro, but of course if you have the influenza, you're going to take Advil, ibuprofen to bring your fever down, right? So the ibuprofen and acetaminophen, Tylenol, are both reversible inhibitors. They interact with an enzyme in dissociable ways and leave the enzyme unaltered once their concentration is low and they're flushed away. But on the flip side, aspirin is irreversible, so it actually kills the enzyme that it binds to. So that takes us through our coverage of enzymes, and I hope it was an awesome ride, because now with our understanding of enzymes, we're going to be able to jump headlong into the canyon, literally, of coverage of metabolism. Good morning and welcome to breakfast. I just enjoyed an awesome plate of eggs and toast and this amazing fruit smoothie with like the whole 9 yards, bananas, protein powder, cocoa, just incredible amounts of nutrients. And so I'm thinking a lot about metabolism. Metabolism could be defined broadly as the network of reactions that are carried out by living cells. And whether you're talking about my body metabolizing my breakfast, or whether you're talking about a microbial cell that also has a network of reactions within the cellular system, we can look broadly at 2 forms of metabolism. Now, the type of metabolism, of course, that I was undergoing most readily just now is called catabolism, because I have taken in some prime nutrients and I am breaking them down. So the breakdown of high energy molecules are carbohydrates and fats and proteins. This process of breaking them down is what we term catabolism. So catabolism, when you think catabolism, think breakdown, oxidation, stripping and ripping high energy electrons off of a fuel source. These are processes that degrade. They degrade larger molecules to liberate smaller molecules and energy. And you can see that I've placed energy at the center of metabolism, because all of these processes are about gleaning and utilizing energy. So in catabolism, the breakdown of these large molecules, for example, the super fantastic wheat toast that I had this morning with my eggs, the carbohydrates, the polymers of monosaccharides were broken down, and they're being broken down in me right now to liberate the smaller molecules that can be utilized both to give energy, right? The process of ripping and stripping high energy electrons off of my toast is, of course, going to the electron transport chain, fueling the generation of a PMF, fueling the generation of ATP. So we know that that energy gleaned, of course, can be used to do cellular work, or to power transport, or to power motion. Remember how the PMF in bacterial cells in good old Norbert can swoosh back in and allow the flagella to rotate as a propeller. Cal's joining for breakfast too. This is Calliope. He's a doll. And so he is helping us think too about metabolism. He was kind of sad because I actually ran out of cat food this morning, so he's not doing as much stripping and ripping. Actually, he has dry food, don't worry. He just doesn't have any wet food, so he's not as spoiled as usual. So stripping and ripping high energy electrons, gleaning the energy for all it's worth from these larger molecules molecules, breaking them down. Sometimes when I picture catabolism, I like think of a big brick building getting subjected to a huge wrecking ball, and the bricks that are liberated from that are the small molecules that are released as breakdown occurs. Now, those small bricks can actually be utilized as molecules that can be built into something else. And we give them a sexy-minded name. We call them precursor metabolites. And these building blocks or precursor metabolites can be utilized in a network of reactions that allows for buildup. So what I didn't tell you is right before breakfast, I went and did our morning ski training. We have an intense run followed by plyometrics, followed by core workout, followed by a strength workout. And so in order to heal from that process and to achieve supercompensation, I have to be running anabolic pathways. So anabolism or buildup pathways is the taking of these precursor metabolites, these building blocks, using them as bricks to build up larger molecules. So anabolic pathways are building pathways. They're biosynthetic pathways. They're the pathways that are using the energy that was liberated from the catabolic pathways to power these buildup reactions. So now, when you think about this, it's really important to think about how you might recognize a catabolic pathway versus an anabolic pathway. Now, of course, our chemists, they're saying, well, Rachel, obviously, I would just be looking for oxidation. If I see a whole bunch of oxidation reactions, that is, if I see the intermediates in a pathway get oxidized and oxidized and oxidized again, I know that we're looking at a catabolic pathway. Now, you may be sexy-minded enough to just recognize oxidation, but guess what? There's a trick. If you recognize that electrons, remember, they don't run around naked in a cell. They have to have carriers, and we know that those molecules, such as NADH and FADH2, those are the pizza delivery carriers of those electrons. So, said another way, if you're looking at a pathway and NADH is generated, FADH2 is generated, you can look at that pathway and say, wow, this is totally a catabolic pathway. This is a breakdown pathway where there's a ton of oxidations happening to generate this reducing power. Likewise, if you see an anabolic pathway where we see that the consumption of those molecules, that is, NADH is used, actually it's NADPH that would be used, then we can say, hey, that's a reductive biosynthesis. It's utilizing those high energy electrons. Now, likewise, another important thing to look at is that catabolic pathways generate energy, anabolic pathways utilize energy. So when we're looking at a pathway that makes ATP, we can say, bing, bing, catabolic, right? If we're looking at a pathway that consumes ATP, that is anabolic, okay? So generation versus consumption of energy. Likewise, generation versus consumption of precursor metabolites. If a pathway takes small molecules and uses them to build up larger molecules, we can see that precursor metabolites are being used in an anabolic pathway. Our Flipped Friday this week is totally going to focus in on the difference between anabolic and catabolic pathways, additionally evoking your earlier knowledge of enzymes and regulation, and we are going to get jazzed about recognizing what pathways are doing, what is their overall goal and objective. So we recognize that in metabolism, energy is central to all of the processes, and that evokes us to talk about the laws of thermodynamics and to begin with energy conservation, or the first law of thermodynamics. That is to say that energy can be converted from one form to another, but it cannot be created or destroyed. And I found the sweetest YouTube video, and we're going to shout out and say thank you to the creator of this YouTube video, which appears to be someone named New Education Chowching, and he has showing us this simple demonstration of the conservation of energy.
Today I'm going to show you an experiment that talks about the conservation of energy. So first of all, you will need 2 weight, alright? Because I don't have 2 weight at home, so I use the red wine bottle instead. And other than that, you will need a scissor, you will need a string. So first, you have to connect the string from one chair to the other. So you can see that it forms a bridge over here. And then after that, tighten the two weights and hang them up on the connections over here. As you can see that these two wine bottles are hanging on the string. Remain still, okay? So conservation of energy tells us the energy will reserve over here, which means it will not escape, or it will transfer to another form of energy. Okay, but the general idea is the energy is transferred from one to the other, and the energy will still be the same. So first of all, I'm gonna swing this red wine bottle and keep this remain still here. Okay, and I'll let you guys to see how this conservation of energy works in this experiment. So I'm gonna swing this. As you can see, this one remains still, and it gains a little bit kinetic energy. And you see that this water bottle, this red wine bottle, actually stays still, and it just transfers back and forward simultaneously. As you can see, this one swings, and this one stands still for a bit, and then this one will steal some of its energy, and it will swing again, and this one remains still. Okay. Hope you guys enjoyed this experiment for.
I love that because it's brilliantly pulling together microbiology with the first law of thermodynamics, because nothing could be more micro than red wine. And so not only is energy conserved in this simple physics demonstration, but energy is also conserved within a yeast cell. So when we think about our system within the biological world, the system is the cell. So it could be that it's a yeast cell, and we know that the total internal energy of the yeast cell could be labeled as its delta E. So that is to say that there are constantly reactions within the yeast cell that are changing the total internal energy of the cell. We call that the delta E. And we know that if that cell undergoes a reaction that releases energy, then of course that energy is not lost, but instead it is gained by the surroundings. So we see the conservation of energy not only in simple physics demonstrations like we saw, but also within a cellular system. Energy lost by the cell is gained by the surroundings. Now, you might be getting kind of sexy-minded about remembering the equation that tells us about total internal energy. So if you are, you're remembering that there's two forms of energy that come together to give us the full equation to express delta E. Delta E, total internal energy change, is equal to delta H minus P delta V. But what's really interesting is, unlike our physics experiments, where P delta V is an important variable, that is the pressure times the change in volume, within a cellular system, the pressure tends to stay relatively constant. So we negate this particular term, and we assume that the delta E is approximately equal to delta H. Now, it used to be that I was that student who thought every time I saw delta H, oh my gosh, and I was a chem major, oh my gosh, that's the thing that I don't understand. But in fact, delta H is really just the change in heat. So the heat loss or heat gain. So in biological systems, we can simplify total internal energy to heat loss or heat gain. Enthalpy is the name of that term. In these biological systems, delta E is due to the cellular reactions that occur in which bonds are broken and new bonds are reformed. And of course, a heat loss or heat gain occurs, and we could simply say a heat transfer. So we can simplify and say that delta E is approximately equal to delta H. So this really does tell us about the heat loss or heat gain within a reaction. And if we think about that, we can give terms to the enthalpy change. And in that, we can partially understand the spontaneity of a reaction. So if you think about what's favorable, heat loss or heat gain, probably most of you are thinking, yeah, heat loss. I mean, that tends to be the favorable direction. And we could say that another way, exothermic reactions tend to be more likely to be spontaneous. But you might also be recalling that there is more than one law of thermodynamics. In order to understand the second law of thermodynamics, I have found a fittingly Valentine's Day themed deck of cards. And we're going to use this, and of course my two cats are here to help me, to demonstrate the second law of thermodynamics. So Joanna, I'm guessing that this isn't the kind of gaming that you're into, but I know some of you are definitely into gaming, so perhaps this will be something that jives with you. But you'll notice that I have ordered the cards in order of suit and number with aces low. So if you kind of go through that whole deck of cards, everything is ordered, everything is completely put into suit, number, and everything is in order. However, if I were to take this deck of cards and shuffle it, and I have to say that shuffling the Hot Lips cards is going to be a little bit tricky, but I'm going to give it my best. And I want you to think about what are the chances that these cards would land again in that ordered conformation. I'm sure you're yelling and saying like 0. It's not quite 0, but it's 1 in 8 times 10 to the 67th. That is, that number in the denominator is greater than the universe is old. So said another way, nature seeks chaos. There are so many more disordered states than there are ordered states. All natural processes proceed in such a way that the disorder of the universe is constantly increasing. Of course, remember that is entropy. So entropy is a measure of the disorder of the system. So we can now put together the first law of thermodynamics with the second law of thermodynamics to entertain the overall notion of reaction spontaneity. And this is measured by something that we call Gibbs free energy, or delta G. So the overall delta G is an expression of overall reaction spontaneity, and it is a function of both the first and second laws of thermodynamics. If a reaction is exothermic and the entropy increases, then we can say without a doubt that this reaction is going to be overall spontaneous. Now, the value of delta G that represents spontaneity is a negative value, and we can figure that out really quickly by thinking about the two terms of enthalpy and entropy. So remember that a heat loss generally tends to be favorable. So if we would reckon, we would see a negative number if we see a heat loss. So we would get a negative number for a heat loss. And then if we see a system whose chaos is increasing, the overall entropy is increasing, then we would expect the term of delta S to be positive. Now, temperature is also always positive because we put it in Kelvin degrees, so we don't see anything below 0 in Kelvin. That's absolute 0. So we would see this term being positive. So then we would get a negative number minus a positive number. So we have minus a minus, or overall a negative number. That is when we know that we have total overall spontaneity of a reaction. Negative delta G values are those values that are overall spontaneous. Now we can look at this in a slightly different way as well. Remember the graph that we drew in which we had free energy as a function of reaction progress? So we now know that free energy can be written as G, or Gibbs, free energy. And then this is just reaction progress on the x-axis. And of course, remember, if we had a reaction in which the reactants were at a higher energy level than were the products, then we could recognize that reaction as being overall spontaneous or energy yielding. And so we can write an equation for delta G that also states things in that way. That is the free energy of the products minus the free energy of the reactants. And if we look at this overall spontaneous reaction where products are at a lower energy state than reactants, we know that this value for the free energy of products will be lower than that for the free energy of the reactants, leaving this as a negative number. So this is another way to look at overall free energy change. So we can go ahead and jot all of that down, reminding ourselves which values of Gibbs free energy are those that indicate spontaneity, overall exergonic reactions versus those that indicate endergonic reactions. So just jotting that down, if we're looking at delta G of less than 0, we know that spontaneous negative values are exergonic or energy yielding. Whereas those positive values, those above 0, those are non-spontaneous and endergonic, energy consuming. So you're thinking, well, this is an awful lot of, maybe bad memories of chemistry and physics. But please do understand that this also relates to everything that we look at and think about with regards to the metabolic pathways within a cell. And if we look at the largest picture regarding metabolic pathways within the cell, we can go all the way back to our equation looking at the glucose molecule or our sugar getting oxidized to form CO2 and water. And if you look at this reaction, a lot of you are thinking to yourselves, yeah, that is me totally chowing down on a bagel or a donut, stripping and ripping the high energy electrons off of that sugar, completely, thoroughly, totally oxidizing it and converting it into CO2 and water, what we breathe out, right? So this is the full and complete and utter oxidation of sugar. Now, others of you who are more chemistry minded, you might be looking at this reaction, you might be thinking, man, that's like if you took a jelly donut, threw it on a bonfire and whoosh, watched it go up in flames and turned to a black carbon crisp. Yeah, exactly. So not only is this the overarching reaction for metabolism, but it is also the overarching reaction for combustion of a sugar, jelly donut on a bonfire. And if we look at the overall delta G for this reaction, we'll notice that it's negative 686 kilocalories per mole. That is to say, overarchingly, this reaction is what? A, exergonic, B, endergonic, C, spontaneous, D, not spontaneous, or is it some combination thereof? And I'll let you take a moment to go ahead and answer that question. And in fact, while you're doing that and thinking about that, I am going to write something else down. Now, of course, I'm guessing that Sean is looking at this reaction and saying to himself, photosynthesis, right? This is the synthesis of a sugar from CO2 and water. So, hey, when we breathe out that carbon dioxide and water, plants look at that and say, woohoo, there is my precursor metabolite and my electron donor. So to enable the both the light and dark reactions of photosynthesis, of course, with the extraction of electrons from that water, there needs to be light to excite them to the top of the ETC to make a PMF, to make ATP, and then that ATP can be used to take the CO2 and use it to build sugar. But when we look at the overall delta G of this reaction, we can look at that and say, wow, that's positive. So photosynthesis, unlike oxidation, is going to be endergonic, non-spontaneous. It's going to take energy. It is an anabolic process, whereas here we're seeing a catabolic or breakdown process. So I hope it helps you in seeing how we might apply our understanding of overall reaction spontaneity to biological systems. There's one more thing we're going to jot down today, and then we're going to break, and you're going to think about getting ready for Friday Flip Day. These values are commonly tabulated, so delta G values are often, you'll find them, like, say, in the back of your book as tabulated values for standard state. And so they'll measure all of these things for varying reactions, and they generally tend to measure it at what we call STP, or standard temperature and pressure. But the thing is that those standard tabulated values don't do a really great job of expressing what's happening within a biological system. Partly it's because when we put everything at 1 molar, that fails to express biological pH, which is, of course, hydrogen ion of 1 times 10 to the minus 7th molar, not 1 molar. And so we can tabulate biological standard state delta Gs, which are delta G naught prime values. However, that still doesn't 100% allow us to understand delta G as it applies to biological systems, because really it's the actual delta G that we want to look at and not this tabulated standard state value. Because in a cellular system, the cell can maintain concentrations of reactants and products in such a way that it may change what the actual delta G is versus the tabulated biological standard state. So really, in a lot of ways, that's a public service announcement more than anything. And I want you to have that basic overarching understanding, such as that we applied in that prior practice question. So can't wait to see you all for a little bit of actual hands-on work tomorrow and Friday Flip Day.